what is a hyperbolic space and what is his isometric group, right?
Yeah,
So
yeah.
even other, I mean, since Bankatas has defined it, I will assume that it has been covered. But nevertheless, I recall. Okay, so the hyperbolic plane is H2, which is the complex upper half space. Okay, equipped with a metric that is coming from a length function, which is ds equal to, it was mod dz by imaginary z. All right. So this is the metric, and this length function defines a metric of H2. So what was the metric? That was, I think, ZW. That was the, you take the infimum of length of all curves from ZW. Okay. So gamma. So you take the infimum over gamma. So curves joining. Okay. So this defines a metric. All right. And this metric, so H2T, this is the Poincare upper half space model of the hyperbolic plane. And this metric is nice in the sense that given any 2 points, you can always get a path that minimizes this distance, and those paths are called geodesic. All right. So between
Yeah, they have sent that through post.
between 2 points ZW in H2, there always exists a distance minimizing path, geodesic joining them. Okay. Sir, is it possible to switch to landscape mode? I mean, it would be a bit problematic for me. You can zoom in, perhaps, if you can. Can you switch on your screen to landscape mode? That may be helpful. Or let me see if I can do it. Is it working? Is it better? I think it is the same, right? Or it is better.
The earlier one was better, I guess.
Okay. So I switch back to earlier one. Thank you. All right. Okay. So this is a, there is a distance minimizing path joining them. All right. And Bankates has given you the geo. So this is okay. So let's not talk about disk now. So I am in the upper half space. So here is my complex upper half space H2. This is the real z equal to x plus iy, y equal to 0. That means this is the real line, and this is my upper half space. All right. Then the geodesics are these lines, these circles, which are orthogonal to the boundary and vertical lines. All right. So these are the geodesics in H2 are semicircles with center on R and vertical lines and vertical lines. All right. So these were the geodesics in H2. Okay. And Bankatesh, did you define the isometry group?
Yeah, yeah. I
Yeah.
defined actually. Yeah.
Okay. Okay. So the group of isometries of H2, it is consist of Z goes to AZ by B by CZ plus P, AD minus BC equal to 1, ABCD in R, union Z goes to AZ bar plus B by CZ bar plus D, such that AD minus BC equal to minus 1. AB, or maybe I think you can take it 1, okay, no problem. Okay, but the point is this whole group has a bijective correspondence with, so, so this is equal to, I call it, this is equal to, m plus 2 union m minus 2, okay, where m plus 2, you can identify it with SL2R modulo plus minus identity. All right. So that means this group, so this is denoted by PSL2R. Okay. So this is the orientation preserving group of isometries. So PSL2R, or we say, okay, that SL2R acts on H2 by Mobius transformations as orientation preserving isometry. So
Krishnendu, I think here in this orientation reversing isometries, this AD minus BC should be minus 1. I think it cannot be 1.
no, the Z bar is there, right?
Yeah,
So actually, what happened? Let me tell you.
yeah, yeah.
Yeah. So m minus 2. Okay. So what happened? M minus 2. So you take f in m minus 2, then fz equal to az bar plus b by cz bar plus d. Now this you can identify with a, b, c, d times the z bar, right? So that is 1, 0, 0, minus 1, something like, or maybe in the other way around, right? So this is 0, 1, 1, 0. I think this is z bar. So as a group, it is what you were saying, but when you take the action, that is az bar plus b by cz bar plus d, where ad minus bc has to be 1. All right.
No, just there is a confusion maybe. For
Yeah.
instance, if you take say this say uh, maybe C is equal to 0, right?
Yeah.
And if you take C is equal to 0, then this the sign of A and D should be same, right? If,
Yeah.
as per your equation, this AD is equal to 1 because if C is equal to 0, this AD has to be 1, right?
Yeah. Yeah.
So
If
AD
C,
has to be so if this AD or A upon D has same sign, this Z goes to Z bar plus something. It is not actually a map from H2 to H2.
okay. Okay. So it is minus 1. All
Yeah,
right.
yeah, 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 yeah,
All right.
yeah,
Okay.
yeah,
Yeah.
yeah.
So the point is that, or alternatively, I mean, what Bankaras is saying, that alternatively, okay, isometry of H2 you can identify with GL2R modulo center of GL2R, okay, which is same as whatever, SL2R mod, uh, yeah, so GL2R has two components, right? So GL2R is okay. If normalized by determinant, then this group has two components. One corresponds to determinant positive, and the other corresponds to determinant negative. So in that sense, you can actually take AD minus BC equal to -1. That's correct. All right. So this is what he covered yesterday. But in this talk, okay, in this talk, we will mostly use the orientation preserving isometries, which are SL2R. Okay. All right. So this is the group that we shall use. So we denote PSL2R as Z goes to AZ plus B by CZ plus D, AD minus BC equal to 1. I mean, it is not needed to write ABCD in R because I mean we are already using this notation. But anyway, so let's use that for the moment. Okay, so this was the upper up space model, and then there is a disk model. So H2. Okay, so H2 can be identified with D2, which is Z in C, such that mod Z equal to 1. You just take this Mobius transformation. That will be a diffeomorphism between H2 and D2, and everything that you learned in H2 can be carried over to D2 as well. All right. So now this is what Bankatesh covered yesterday. Now there was a question about Euclidean circle and hyperbolic circle. Okay, so now one small observation I mean I would just like to make here, that recall complex analysis, or better say recall complex Mobius transformations. Z goes to AZ plus B by CZ plus D, where AD minus BC is still 1, but ABCD belongs to complex numbers. Okay, then this corresponds to the group SL2C, but the crucial fact complex Mobius transformations are conformal, that is angle preserving. Okay, so by angle I mean that you take one point, then take a curve through that point, then you can always define one angle between the tangential curve at that point, and that is what so angle means you have two curves. So this is the picture. Just let me draw quickly. So suppose these are two curves, then you just draw the angle between the tangent at these two curves. So this is called this is the concept of angle at a point when you have two curves. And one crucial fact in complex analysis is that the conformal transformations, the complex Mobius transformations are conformal, so they are angle preserving, and a complex Mobius transformation Z goes to AZ plus B plus CZ plus D. Just give me 1 minute. Hello? Hello?
Yeah.
Yeah.
Yeah. Am I audible?
Yeah. You are
Yeah.
audible.
Okay.
Yeah.
So my slide has changed, I see. So a complex Mobius transformation is okay, preserves the extended real line if and only if A, B, C, D are real numbers. So this is sort of, gives you the feeling that SL2R is the right candidate for the isometry group. And because they preserves the angle, intuitively that is also the reason that a Euclidean circle and hyperbolic circle, their shapes are the same. All right. And, this is also justify to some extent that why any two hyperbolic triangles with same angle are congruent. Okay, so this was a slight digression, but my aim here is not to discuss all this. So I will now come back to the point, which is about uh, so far, any question? I just recall whatever was covered yesterday. Okay, so if there is no questions, let me just quickly now start my main topic of lectures. So today I will give you a gentle introduction about discrete subgroups of PSL2R, and then tomorrow I will discuss what is the Teichmuller space and how they are related to hyperbolic geometry. All right. So today's the first topic is classification of isometries. So Bankatesh, did you cover it yesterday?
No. I
No.
have not covered.
All
Yeah.
right. All
I
right.
just defined the isometry. Yeah.
Okay. Okay. So first note. So take any Mobius transformation. Z goes to AZ plus B by CZ plus D. Then Fz equal to Z has at most two solutions, right? So you can easily solve Az plus B by Cz plus D equal to Z. That will give you this quadratic equation. And you know what is Z. That is A minus D plus minus root over. It will be B square minus or plus 4BC. Minus 4BC, I have to calculate. I think D minus A minus B, right? So B square,
Yeah,
what will be
plus.
plus
Yeah.
plus 4BC by 2 C, right? Yeah. So then if you break it up, what it will give you? So this is A minus D plus minus root over. This is A plus D square minus 4. by 2c. All right. So these are the fixed points. So this means every isometry of H2 can have at most 2 fixed points. Okay. So 2 fixed points on the complex number. So because we are solving a complex equation, so the solutions will be complex roots. So it can have at most 2 fixed points on C, and if z equal to e to the power I theta, then okay, z equal to, say, you can see, I mean, so if z is non-real complex numbers, then it appear in complex conjugates. All right. So this gives you the classification of isometries in 3 classes. Okay. So now definition. Okay. So, and isometry F in PSL2R is called elliptic if it has a unique fixed point in H2. Now note, in this case, Z is a complex number. All right, it is parabolic if F has a unique fixed point on the boundary. In this case, okay, so I would say this polynomial as 1. In this case, 1 has a real root of order 2, and it is called hyperbolic if F has exactly 2 fixed points on del H2, that is, 1 has 2 distinct real roots. All right. So this is a trichotomy of classification in terms of into elliptic, parabolic, and hyperbolic isometries, and they are mutually exclusive. And as you can see that when you solve this quadratic equation 1, these are the only possibilities. So every isometry of the hyperbolic plane is either of these 3 types. Okay. So any F in PSL2R is either of these 3 types. Okay. So this is a classification in terms of fixed points. Now, algebraically, what is the classification? So this is a dynamical classification, right? But in this case, this dynamics is very much nicely related to the algebraic information of the group SL2R. So in group theory, I mean, so I think everybody knows here. So the above, yes, yes,
Sir, what do you mean by dynamic here? Dynamic classification?
fixed point, the way it behaves on the space. So it has fixed points, right? So every isometry has either one fixed point or two fixed points, and where the fixed point lies. So that's what I mean. Okay.
Okay, okay.
Yeah, and actually, I am not getting into that, but it is a interesting, observation to see how the isometries behave when you iterate them. That means if you take the cyclic group generated by each of these three transformations, how their orbit looks like. There are nice pictures that you can try to find out. Okay, so that I'm not discussing here, but it's worth looking at the pictures, how they behave. Okay. Now the above also gives a conjugacy classification of isometries. Now, how do you get that? So so we will discuss how you can get conjugacy classification of isometries of the hyperbolic plane from this classification. But before going that, I would like to recall two facts about these isometries. So I hope everybody is familiar here with group actions, right? Everyone knows what is a group action, yeah? I am sure, I mean, everybody knows what is a group action here. And one more information I would like to know, that does everyone know covering space theory also? Hello?
Maybe not, Krishnendu. So
Oh, not everyone knows covering space theory, yeah?
yeah.
Okay, okay.
PhD students will know, I guess. MSc, some
But
of them may
it
not.
is a lecture, so I should not assume it. And that's why.
Yeah.
Okay, okay, fine.
Yeah.
Fine, no
Hello.
problem. Yeah.
Sir, on the behalf of fixed point, you classify these all things hyperbolic, elliptic, and
Yes.
parabolic.
Yes.
But what is the intuition? This call hyperbolic or elliptic or
Oh,
parabolic?
there is no proper intuition actually. Okay, I mean this question lots of people have asked me. So probably if you look at their dynamical pictures, that will give you some idea why they called it. But I think it is just a I think analogy with classical geometry. So in classically there are three types of geometry, right? Elliptic, parabolic, and hyperbolic. All right. So elliptic geometry means geometry of the sphere, and parabolic geometry means geometry of the maybe the extended, I mean, of the Euclidean plane that you can think of as a particular case of parabolic geometry, perhaps. And hyperbolic means hyperbolic, right? So here, if you see that the fixed point, I mean, if you see the conjugacy classification, probably it will be more clear to you. Okay. So let's wait for the conjugacy classification that I am going to discuss, and then maybe I can make some more intuitive comments on that. Okay. All right. So now, before giving the conjugacy classification, okay, So conjugacy classes of isometry. Or perhaps let me write down the result first. Okay, so theorem. Let F in PSL2R, okay, then F is conjugate to a transformation A in PSL2R that is induced by one of the following matrices in SL2R. Okay, so if so, first of all, F is plus minus identity. This is the trivial case. Okay. So then F is, if F is elliptic, so am I there? Yeah. If F is elliptic, it is, so I mean, even though I am writing in terms of matrices, but when I am saying that F is conjugate to, say, a matrix of this form, what I really mean is that F is conjugate to a transformation that is induced by a matrix of this form. Okay, so just keep that in mind. Okay, so I have included plus minus identity, so I can safely make it strict. Okay, and if F is parabolic, imply F is conjugate to 1, 1, 0, 1. Okay, so there is a unique conjugacy class of parabolic isometries, and if F is hyperbolic, then F is conjugate to a matrix of the form, okay, where you can take R greater than 1, or you can take maybe up to you. All right.
Krishnendu,
Yeah.
all of them are isometry on H2, right?
Yes, yes. So,
Which is not the case as real on
no,
R2.
so that means what I mean here, since you have mentioned it, so conjugate to F theta, or maybe conjugate to A, okay, of this form, okay. So A is induced by a matrix of this form. So in this case, F is conjugate to Z goes to Z plus 1, or Z goes to Z minus 1, or F is 1 minus 1, 0, 1. Okay. So these are all isometries of H2. So what I'm doing here, then that is F is Z goes to R square Z. Okay. So what I'm doing here, so this gives a conjugacy classification of isometries. That means up to conjugacy, the isometries of hyperbolic plane are either of these types. Okay. So now I will sketch a proof of this fact, that how one can say such a strong result, that you take any arbitrary isometry and it is essentially saying that it's enough to look into these prototypes, either these rotations, which are elliptics, or these translations, which are parabolic. So take any parabolic isometry that will be either of these two, that will be conjugate to either of these two types of translations. And if you take any arbitrary hyperbolic isometry, it will be conjugate to the stretch maps. All right.
So,
So,
Krishnendu,
yeah.
are you also considering the boundary also, or only hyperbolic plane? I think you are also considering the boundary.
The boundary is, of course, boundary is preserved by the SL2R, no?
Yeah,
And
yeah,
when I, yeah. So,
yeah,
when I say here that
yeah.
it has at most two solutions, the solution can lie in the boundary. Okay. So you
Yeah.
see, initially we take solution in C, but then I remark that either they are complex conjugates or they are real numbers, right? If they are real, then that's the boundary of the hyperbolic plane. Okay. So in the definition, I have written that if it has a unique fixed point on the boundary.
Yeah.
Yeah. So of course, I mean, we
Yeah,
are
yeah.
considering boundary. Yeah. Okay. All right. Okay. Okay. So let me try to sketch the proof of this result. Okay. Sketch of the proof. Okay. So to sketch the proof, what I really need to know is maybe I prove a lemma. So before that, recall a definition. Okay. Definition. Let G be a group acting on a set X. Then G action is called transitive on X if for all pair XY in X, there exists G in G such that Gx equal to Y. All right. So this is the notion of transitive action. Okay. And the crucial lemma for us is the following. Lemma the group SL2R acts transitively on H2. Okay, the proof is very easy. I will quickly prove it. So the proof, okay, so take Z equal to A plus IB in H2. Okay, I take B greater than 0, of course, because we are in H2. All right. Okay. Now consider A equal to B by root B, then A by root B, 0, 1 by root B. Okay, consider this matrix. The induced isometry is, I denote it by, again, A is Z goes to AZ plus B. Okay, now observe A maps I, well, not AZ plus B, it will be BZ plus A. And A of I will be Z, right? So that means on the hyperbolic plane, you take, okay, let me draw the upper space. So you have the hyperbolic plane, and here you have a point I. Now you take any point Z, you always get one isometry that maps Z to I. Now take another point W, you get another isometry that maps I to W. So you compose A and B, you always get a isometry that maps Z to W. So these imply that for all this G in PSL2R such that Gz equal to W. Okay. So every so PSL2R acts transitively on H2. Okay.
Sir, voice is not clear.
Yeah.
No, it's okay. It's
Yeah. Yeah.
okay. Yeah.
Hello.
Yeah.
Yes.
Yeah.
Oh, my voice is not clear. Okay. Okay. Okay.
Yeah. Yeah. It's fine. Yeah.
So now fine. Okay. Okay. So maybe it's an isolated problem, or there was a problem.
No, no, it is okay. I think. Yeah. Now it is
Okay.
okay. It's perfectly fine. Yeah.
Okay. Okay. So PSL2R acts transitively on the set of geodesics of H2. So it's not only transitive on the set of points, it also transitive on the set of geodesics. Okay, now proof. So let me change my slide. So proof. Okay, so here I have the upper space. All right. So now this is my y-axis, right? Where x equal to 0. Now what we would like to show that if you take any other geodesic L, you want to map it to this y-axis. Okay. So now there can be two cases. Okay. So case one, L is a vertical line. So you have here x equal to 0 and you have here L. Now this is, suppose this point is C, this is 0, right? Then you just map Z goes to Z plus C or Z minus C. So you can map one vertical line onto other vertical line. So done. Okay. Now case 2. You have here x equal to 0 and here you have L, which is a semicircle perpendicular to the real axis. Now suppose the endpoints are A and B. Okay, then Z goes to Z minus A by Z plus B. Okay, this maps L onto the line x equal to 0. So this completes the proof. Okay, now you see this statement is strong. It is saying that PSL2R acts transitively on the set of geodesics of H2. Now, in hyperbolic plane, the endpoints of a geodesic determine a geodesic. Okay, so as a corollary, this also shows that SL2R acts doubly transitively on boundary of H2. All right, so that means you take any pair of points. So that is, it means that is pair of points on del H2 are homogeneous. That means you always get a isometric. So lemma SL2R acts triply transitively on the boundary. Okay, so that means you take, that is any, okay, that means any triple of points x, y, z mapped onto any other triple by an isometry. Okay, and proving this is not difficult. I hope, I mean, in the complex analysis, everyone knows what is a cross ratio, right? So essentially, cross ratios will do the job. So proof cross ratio of 3 points 0, 1, infinity will do the job. Okay, so this is just a remark, but the concrete construction, you know, I mean, one has to work it out actually. Okay, but I am just leaving. Okay, leaving the proof. So maybe I just write down the transformation. It's not difficult to write down. Okay, so assume A, B, C in R. Okay, A greater than B greater than C. Suppose A not equal to infinity. Okay, then you have a transformation of this form, which is A minus CZ minus B A minus C by B minus CZ minus C B minus C. Okay, so f of C equal to infinity, and the other case is similar. Okay, A on the boundary and the hyperbolic space is really very nice. It's transitive, it's doubly transitive, it's triply transitive, and so on and so forth. And the conjugacy classification that I am talking about comes essentially from there. Okay, so let me quickly sketch the conjugacy classification. Okay, so sketch of suppose G equal to HF, H inverse, then what is the fixed point equal to? That is equal to H of fixed point set of F. All right, so this is a small observation. So that means elliptic, parabolic, give mutually disjoint classes. Okay, then you observe that suppose F is parabolic. Now by transitivity, okay, just a minute. Parabolic, let me just show you one and the rest I leave. Okay, so let F be parabolic with fixed point that maps P to infinity. Then HF, H inverse fixes infinity. Okay, so that is HF, H inverse is of the form AB 0D. Okay, so now it has a unique fixed point. By of the fixed point A equal to D equal to 1 or A equal to D equal to -1 if you want. Okay, so every element, so every parabolic is conjugate to 1B01. Now it is easy to see that one can further conjugate it to 101 or 1 minus 101 T1 T2, and that T1 cannot be conjugated to T2. Okay, so that means every parabolic isometry is conjugate to one of these two types. Similarly, one can see for the others. Okay, now let me now come back to the statement of the conjugacy classification where I started with. Okay, let me not come back here. Let me do it here itself. Okay, so you see that, so the summary, okay, the conjugacy in PSL2R. Okay, okay, so elliptic if and only if it is conjugate to cos theta minus sin theta cos theta, parabolic if and only if conjugate to 1 1 0 1 or 1 minus 1 0 1, and hyperbolic if and only if conjugate to R 0 0 R inverse. Now think in terms of matrices. Okay, so these matrices have some unique conjugacy invariants, which are the trace. Now you can, so let call it, let take say A in SL2R. Suppose it induces if and only if, so A induces elliptic isometry if and only if the absolute value of the trace of A is less than 2. In case of parabolic, the trace of A will be always equal to 2. And in case of hyperbolic, the trace of A is greater than 2. So that means if someone gives you an element from SL2R, you can tell about their fixed point behavior just by looking at the traces of the corresponding matrices. And that precisely gives you the conjugacy classes in the groups also. So here, even though we are doing hyperbolic geometry, but from there one can also extract group theoretic information about the isometries. Okay, so this gives you the conjugacy classification. So Pankajas, is it a 1 hour talk or 1.5 hour?
It's up to you actually. If you think that we can stop, you can stop. Otherwise, if you want to continue, it's not. Yeah, it is up to
Okay.
you. Yeah.
Maybe I just introduce what are the discrete subgroups.
Yeah,
Okay,
yeah, sure,
and
sure.
then probably I will stop. All
Yeah,
right.
yeah, yeah, sure.
So you see, being a group. Okay, so discrete subgroups. Now PSL2R is SL2R mod plus minus identity. Okay. Now elements of PSL2R are AZ plus B by CZ plus D, or in other words, you can consider it as something inside R4. Okay, so you can get PSL2R as some sort of quotient of R4. So SL2R is a closed subset. So closed subset of R4. Now from this, one gets a topology on PSL2R and a norm. Okay. One can also define for T norm of T to be the usual norm from R4. Okay. And this topology, the group operations will be continuous. All right. So this implies PSL2R is a topological group. Okay. Now a subgroup of PSL2R is called discrete, a subgroup, say gamma, if the induced topology on gamma is discrete topology. Okay. Now that is if and only if. Okay. So if and only if you take a sequence from gamma a discrete we are interested in understanding discrete subgroup.
Yeah. Actually, your
PSL
voice
let me
is
take 5 more minutes.
your
Okay.
voice is
So
was not
I
coming.
define
I think for the last maybe 1 or 2 minutes.
oh, okay. So actually, I moved myself from the laptop
maybe
a
just
bit.
repeat your
So
last
that's why. Now it is
comment.
fine. Let me go to my. Okay. So now the voice is good, no?
Yeah, it's good.
Now the voice is
Yeah,
fine,
its
right?
voice is fine.
Yeah.
You
So
maybe
a
you
subgroup,
just you must repeat your last comment on
yeah,
the last
subgroup
expression.
gamma. Yeah. The subgroup gamma of PSL2R is called discrete if the induced topology on gamma is discrete. All right. So equivalently, gamma is discrete if you have a sequence Tn from gamma which say converging to identity, then Tn will be equal to identity for sufficiently large n. Okay. So in other words, if identity is a open subset, right, in the discrete topology in gamma, then it is discrete. All right.
Yeah.
So this is the definition of discreteness that I have made. Now, definition, I mean, I just said, so definition. Okay. So a discrete subgroup of PSL2R is called a Fuchsian group. Okay. So now I will end by a characterization of Fuchsian group. For that, I will make another definition. Now, this definition is actually not specific to this hyperbolic plane geometry. So I will make the definition very general. So let gamma be a group acting on a metric space xd by, okay, I mean, I don't need the metric actually. Actually, you can define it for any topological space. Okay, acting on a for the but I take metric space. I think that's nice space. In arbitrary topological space, one may have to formulate it nicely. Oops. So let gamma be a group acting on a metric space X by homeomorphisms. Okay, then gamma is said to act on X properly discontinuously if for all compact subsets K inside X, the set is finite. Okay, so that means you take any compact subset of X, then the elements of gamma that intersects K in a non-empty way, that can only be finitely many in numbers. All right. And another definition. So gamma acts freely on X if for all gamma in gamma, if gamma has a, okay, for all gamma in gamma, if gamma not equal to identity, then gamma x not equal to x for all x in X. So that means all non-identity element of gamma act without fixed points. So if that is the case, then gamma acts freely. All right. So now,
Sir, is
yeah,
it necessary to that the group act on matrix space?
no, not necessary. But you know,
Okay.
if I say topological space, then I have to assume house drop, second countable, etc.
Oh, okay, okay. Yeah.
I don't want to write those things. Okay, so metric space is nice, right? So it satisfies all the properties of a topological space where it can define. So that's why I take metric space. All right.
Yeah.
Okay. Yeah. Now what happened for us? So it's a theorem. Okay. So this theorem actually I would not be able to prove here, but let me state it. So let gamma be a subgroup of PSL2R. Then the following are equivalent. That gamma acts freely and properly discontinuously on H2. Gamma is a gamma is a Fuchsian group without any finite order element. Okay, and H2 mod gamma, I will define it So this is house drop, and the projection map is a covering transformation. I think if people don't know covering space theory, they can just ignore the last sentence. But what is the punchline here is the following, that a group is acting properly discontinuously on freely on H2, that is equivalent to say that it is a discrete subgroup of PSL2R. And this is important information. Now, what is a covering transformation? I will not say that. But what is H2 mod gamma? Let me just say this. So H2 mod gamma is the orbit space. Okay. So it is gamma of X. So the space of
Krishnada?
consider H2 mod gamma. Yeah.
Yeah. I guess you meant this to be a
Yes.
covering map, right? Not transformation. I think
What is the
covering
difference?
transformation means it's a deck transformation.
Oh, I see. I see. Okay. Okay. Covering map. Yeah. This is a covering. All right. Okay. Yeah. So I think with this theorem, I will end today, and I will start tomorrow. Yeah.
I have some questions. So I
Yes,
have
yes.
5 minutes. I want to go. So one question is, Fuchsian group is just a word for discrete subgroup of SL2 R, right? I mean
Yes.
PSL2 R.
Yes. Yes.
Secondly, they are not all lattices, right?
No, 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 no.
Because
Lattices
anyway,
are
yeah, much smaller class. So even if the dimension
and
is
yeah, and the lattices
even if,
does not act freely and properly
Oh.
discontinuously, right? The lattice
no,
may have
I
torsional
see.
element,
Lattices
no?
don't. SL2Z will not act freely and properly discontinuously.
SL2Z does not act on H2. It acts on the torus. Yeah. Hello. No, but SL2Z is a yeah. It will act freely and properly discontinuously on H2 also, and it has a nice fundamental domain. Hello. Yeah. So
Christian,
it is a yeah. So SL2Z acts on H2. Okay. So the action is certainly properly discontinuous, and it's free. It's not free. It's not free because SL2Z is Z2 star Z3, right? So there is no torsion element. There is a torsion element there, right? Which is Z2. So there is order 2
no,
element
you can
there.
take PSL2Z, right? I mean,
Yeah. So that should work. That should work.
because you see, you're just saying that if it acts freely and properly discontinuously, it is equivalent to saying that gamma is a Fuchsian group without finite any order relevance. Okay, I see. Okay, SL2Z does have a lot of finite orders. So you have to go to a subgroup of finite index then, which is anyway fixed point. I mean, it does. Yeah, you can use
Yeah.
Selberg's lemma or something.
Yeah. I think the action of SL2Z is properly discontinuous, but it is not free.
Yeah, but you can go to a subgroup of finite index which does not have free torsion elements by Selberg's lemma. So that would do. But these, So, but what is the fundamental group of H2?
Yeah, so H2, that's a good question. So I am going to talk about it tomorrow. So the fundamental group of H2, not H2, but fundamental group of H2 mod gamma is gamma. If this is
Oh, yeah, okay. So anyway, so I have to run. So I have another meeting, and I hope you will have tomorrow's lecture recorded and put on the website. I may not be able to attend. Thank
Yeah.
you. So, yeah.
Okay. Thank you
Bye.
for asking.
Mhm.
Bye. So any more questions?
Any question
Yes.
from any other participant? Feel free to interact actually. Yeah.
Sir, what is the meaning of properly discontinuous on H2? I not.
This is just definition, I think. Yeah.
Yeah. So you take any compact subset, then the set of all elements from gamma that intersects this compact subset in a non-trivial, in a non-empty way.
Okay.
Yeah. So if this seed is finite, then it is properly discontinuous.
Okay.
Okay.
Maybe it's better to find some examples and some non-example. Then it one can better
Yeah.
understand. Yeah.
Yeah. Yeah. Yeah. But yeah. So maybe I can make one more comment that maybe I will do it tomorrow. That whatever other comments we needed. Yeah. So
Yeah.
so the point is that if you take any abelian Fuchsian group, then it will be always a cyclic group. Okay. So in other words, no Fuchsian group will be isomorphic to Z cross Z, to Z2. Okay. And this is useful. So maybe I will resume tomorrow. I will give one or two
Sure.
more about Fuchsian group, and then I will briefly discuss what are the Page-Muller spaces, which was the main title of my talk, right?
Yeah.
But
Okay.
two lecture is a bit short time for covering.
Yeah. I think so. Yeah.
Yeah.
So, but yeah, actually, all the participants have much time actually. So
they can get a flavor and they can pick it up.
certainly. Yeah. And they can interact also after these series of lectures also. Yeah.
Right, absolutely.
Okay, so thank you, Krishnendu. So maybe today we finish and we'll meet tomorrow.
Okay, great.
Okay, thank you. Bye.